Okay. Good morning, everybody. All right, so let's get started. Today I'm going to be introducing just the basic principles of kinetics. This is pretty much undergraduate material, and you probably are all familiar with it, but anyway, we'll just go through it again. So I'm going to talk about first and second order reactions, kinetics and flow reactors, plug versus stirred reactors. And I'll be talking about the use then of rapid compression machines and shock tubes also for kinetic studies. I'll be talking about the temperature dependence, the Arrhenius equation, and then complex reactions, a little bit about that. Okay, so I mentioned this yesterday, and here's our diagram again. Again, this should be an equilibrium arrow. But we have, if we take any container or reactor and we put species A into the reactor, that species then it can decompose to produce B. Okay? And so this is the concentration versus time profiles that you would get for A and B. Okay? And the time here is arbitrary. Okay? So you can see A decreases in time, B increases in time, and at a certain point, indicated by this dotted line, this is a repeat of what I said yesterday, the system reaches equilibrium, where the rate of the forward reaction, the rate reverse reaction are equal. Okay. So one thing I do want to say, and I said it yesterday and I want to highlight it again today. When I'm talking about kinetics and looking at rates of reaction and so on, I'm always talking about very early stage of reaction, where the concentration of B is negligible, okay? And I'll explain why in a minute, okay? But always bear that in mind, that we're talking about very early stages of reaction, okay? So I do refer to this part as being kinetics, this part being equilibrium. But even when I talk about the kinetics now, I'm talking about the very early stages of reaction, okay? So, and even not out to here, but in here. Okay. So if we look at the rate of reaction, it depends on the concentration of reactants. And this picture is actually taken from Wikipedia, okay? If we have low concentration, we have few collisions. High concentration, we have more collisions. And that makes sense, okay? So we can say the rate of reaction is proportional to concentration. And I think we can just, with the picture, we can just see that, right? It's logical, all right? But we know also that if something is proportional to something else, then that something is equal to a constant times that something else, okay? And so the rate is equal to the rate constant times concentration, okay? And so as a kineticist, okay, I tell people, look, I'm a rate constant determiner, okay? If I'm looking at kinetics of reaction, really kineticists are rate constant determiners, okay? Because typically, you know the concentration of the species, right? And so to measure the rate, what you're doing is you're measuring the rate constant, okay? And that's the essence of chemical kinetics. What is the rate constant for reaction, okay? So I think this is a nice slide for that. It's nice and simple, but the focus is really always on the rate constant. Okay, and so here, and I think it's pretty straightforward. So here's a sample reaction. We have 5 moles of Br minus plus 1 mole of BrO3 minus plus 6 moles of H plus, giving us 3 moles of Br2 and 3 moles of water. Okay, and what is the rate of reaction? So we put Br minus, O3 minus, and 6H plus into a container, right? And we have 100 arbitrary units of each one, okay? What is the rate of reaction, okay? So the rate, if we monitor it, is minus 1/5 the rate of change of Br minus with respect to time, or minus 1/6 the rate of change of H plus with respect to time, or minus 1/1 the rate of change of BrO3 minus with respect to time, or plus 1/3 the rate of change of Br2 with respect to time, or plus 1/3 the rate of change of water with respect to time. So we can monitor the rate of reaction by following any one of the reactants of products, right? That's a thing. But you can see that also it follows the stoichiometric coefficient. So the rate of one reaction, as the reaction is written, we know that 5 moles of Br minus is used in one reaction. So if we're monitoring the reaction, we'll see after a unit time, we'll have 95 moles of Br minus left. After the next arbitrary unit of time, we'll have 90 moles of Br minus left, okay? So each reaction uses 5, okay? And it's the same then with H+. We would have 94 after 1 arbitrary unit of time. We would have 88 after 2 arbitrary units of time, and so on. And that's, hence we use the stoichiometric coefficient to determine the rate of reaction. Okay? Okay. Okay, so, and these are all equal to one another. I haven't included the BrO3 minus, but that's also should be there, okay? Or we say, right, the rate is equal to the rate constant times the concentration of Br minus to the alpha, BrO3 minus to the beta, and H+ to the gamma, okay? And by experiment, it's found that alpha is 1, beta is 1, and gamma is 2, okay? So this is the rate law, okay? And we can put a little F underscore there if we want and say, right, the rate is equal to the rate constant in the forward direction times the concentration of the reactants, raised to some power, okay? But it's actually not true. The rate is equal to the rate constant in the forward direction times the concentration of these guys, minus the rate constant in the reverse direction times the concentration of the products, okay? That's the net rate, right? So bear in mind, as I said at the very start, when I'm talking about the kinetics here, I'm always talking about the very early stages of reaction, when there's no appreciable concentration of product, okay? We're just focusing on that very early stage. It's a little bit unrealistic, but we just want to keep it pure kinetics, okay? All right, so, and then if we have then any equation, we have m moles of A plus n moles of B, giving us p moles of X and q moles of Y. The rate is minus 1 over m, the change in concentration of A with respect to time. It's minus 1 over n, the change in concentration of B with respect to time. It's plus 1 over p, the change in concentration of X with respect to time, and plus 1 over q, the change in concentration of Y with respect to time. So you can see that the rate is negative. It's minus 1 over the stoichiometric coefficient for reactants and plus 1 over the stoichiometric coefficient for products. Why? Because dA dt is negative for reactants. So we have minus times minus, which is plus. So the rate is always positive, okay? And the units of rate are concentration per unit time, okay? So because you're looking at change in concentration per unit time. In SI units, it's moles per meter cubed per second, but more practically, moles per decimeter cubed per second. Okay. So how does the rate depend on concentration? Typically, we find out by experiment, right? So the rate law we give as equal to the rate constant to some order rate constant, times the concentration of A to the alpha times B to the beta, and so on. Okay? So the total order then is the sum of the partial orders related to the reactants. Okay? So if we have C to the gamma, for instance, the total order would be the sum of alpha, beta, and gamma. Okay? In this example, it's just the sum of alpha and beta for A and B. Okay? And we have the rate constant is K subscript n. And the rate is equal to the rate constant when every concentration is unity. Okay. But here, how do we get the experimental rate law? Or here the the rate law is provided, I should say. And we have this reaction, CO plus Cl2 gives us CO, Cl2. Okay? And the rate of that reaction is equal to the rate constant times the concentration of CO to the alpha, where alpha is 1, and Cl2 to the beta, where beta is a half. Okay? And the total order of that reaction is 1 plus a half. It's 1.5 order, or 1.5. Okay? For H2 plus I2, giving us 2HI, the rate is equal to the rate constant times the concentration of H2 to the alpha, alpha is 1, times I2 to the beta, beta is 1. Okay? The total order is 2, 1 plus 1. Right? And here we have H2 plus Br2 giving us 2HBr. The rate is equal to the rate constant times the concentration of H2 to the alpha times Br2 to the beta, all over 1 plus K prime times this value here. And the order here is complicated, so it can't be defined. All right. Okay, so where do we get the rate law from, or the rate from? Okay. So if we define the rate is equal to 1 over the stoichiometric coefficient times the change in concentration of the species with respect to time, and that's equal to the rate constant times the concentration of A to the power of n. Okay? So n is the order. Okay? This is just overcomplicating things. We just take this expression to start with, right? I'll go back. I'm going to revisit this a little bit later anyway. Okay, so I'm not going to talk about it now. Okay? So let's say we have A giving us products, and this is a first order decay. Okay? Then we have the rate is the change in concentration of A with respect to time, and that's equal to minus the rate constant times the concentration of A raised to the power of 1. Okay? It's first order. Okay? So then we can rearrange and we say, okay, the change in concentration of A over the concentration of A is equal to minus K times dt. So the integral from the concentration of A at time 0 to the concentration of A at time t, the change in the concentration of A over the concentration of A is minus the rate constant times the integral from time 0 to time t dt. All right? And so the integral of 1 over x dx is the log of x. So we have the log of the concentration of A at time t minus the log of the concentration of A at time 0 is equal to minus k times t minus t0. Okay? So we just rearrange this. We have the log of A at any time is equal to the log of A at time 0 minus kt. Okay? So for first order reaction, if we plot the log of the concentration of a species at any time versus time, we should get a straight line, the slope of which is minus the rate constant, and the y-intercept is log of the concentration of A at time 0. Okay? And this is what we see. Okay? So we have log of concentration of A on the y-axis versus time on the x-axis. We get a straight line, the slope of which is minus the rate constant. So the rate constant in this case is 1.49 times 10 to the minus 3 per second. Okay? The units are inverse time. Okay? Because the units of log of anything are unitless. Okay? So it's inverse time. Okay. Now, so we have this expression, but we can also express it like this. So we have log of the concentration of A at t over A0 is equal to minus kt. So then we can get the concentration of A at any time is equal to the concentration of A at time 0 times the exponent of minus the rate constant times t. And this is the version of the equation, we'd say, that's used for carbon dating. So if you know the concentration of carbon-14 in a sample, we know the rate at which carbon-14 decays, we can actually determine the lifetime of the sample. Okay? And we know the date of that sample comes from. Okay? So that's how that is used. This expression is also, well, I'll say it in a minute. Okay? So you can see here that the concentration of A at any time is exponentially dependent on time. Okay? Well, and that's obvious because of the log. This is more for undergraduate class, right? So you can see that the concentration of A exponentially decreases with time, okay, if it's first order. Okay? And so when is a reaction over? okay? And technically never, only at infinite time, okay? But appreciably after a reasonably short time, relatively short time, okay? Because it's decreasing exponentially, okay? So but technically it's never over, okay? So then if we think about the half-life of a first-order reaction, the half-life is the time taken for the concentration of a sample to reach half its original value. That's the half-life, okay? So we have this expression, and we use this expression. We say, okay, log of a half the concentration of A at time 0 over the concentration of A at time 0 is equal to minus the rate constant times the half-life, okay? And we can see clearly here the concentration of A at time 0 and will cancel. So we have the log of a half is equal to minus K times T a half for the half-life, okay? So we have the half-life is 0.693 all over the rate constant, or the rate constant is 0.693 all over the half-life for a first-order reaction, okay? But this is actually very nice expression to use, or it's the expression to use. So say, for instance, you're told, look, a sample follows first-order decay, and after so many minutes, 10% has decomposed. At what time will it be 90% decomposed? Use this form of the expression to solve that problem, okay? It makes life very easy. Okay, so that's first-order kinetics. So if a species obeys first-order decay, you plot log of its concentration versus time, you should get a straight line, the slope of which is minus the rate constant. Okay? What about if a species obeys second-order decay? So here we have A giving us products, A moles of A giving us products again, and we say the rate is the change in concentration of A with respect to time, and that's minus the rate constant times the concentration of A to the power of 2. Okay? So it's second order this time, right? And then if we integrate that, we have 1 over the concentration of A squared dA. Okay? So the integral of 1 or of x to the n is x to the n plus 1 over n plus 1. Okay? So this is, if we integrate that, we have 1 over the concentration of A at time 0 minus 1 over the concentration of A at time t is equal to minus k times t minus t0. And we rewrite this, so we have 1 over A at t minus 1 over A0 is equal to plus kt. So we then write 1 over the concentration of A at any time is equal to 1 over A0 plus kt. Y is equal to mx plus c. Okay? Or y is equal to mx plus c here. So if we plot 1 over the concentration of A at any time versus time, we should get a straight line, the slope of which is equal to the rate constant, and the y-intercept is 1 over the concentration of A at time 0. Okay, and here's an example. So this is just for this compound decomposition. We have concentration in 1 over concentration, so it's liters per mole, versus time. And we plot 1 over concentration versus time. We see we get a straight line. The y-intercept is 1 over the concentration of A at time 0. Okay? And the slope is 1.374 times 10 to the minus 1 liters per mole per minute. Okay? So that's the rate constant. Okay? So the units then, again, are the units of y over x. But in this case, the units are of y have units. It's liters per mole, inverse concentration per unit time. Okay? Okay, and if we get this half-life of a second-order reaction then, we have 1 over, we have this expression. So the concentration of A at time t is a half A0. So we have 1 over a half A0, which is 2 over A0, minus 1 over A0 is equal to the rate constant times the half-life. So we can say 1 over the concentration of, the original concentration of A is equal to the rate constant times the half-life, or 1 over the rate constant times the concentration of A at time 0 is the half-life. Okay. for a second order reaction. Okay. Okay, so that's one way of determining the rate law of reaction. You can integrate. Okay? So, and you can do that by trial and error. So, say for instance, you're given, here are the concentrations of a species versus time. Determine whether the reaction is first order or second order. So what do? You plot log of the concentration versus time. If you get a straight line, you know the species obeys first order decay, and you can get the rate constant. It's minus the slope. Okay? If it isn't, then you plot 1 over concentration versus time. That will probably give you a straight line, right? And you know then that the species obeys second order kinetics, and the slope of the line is the rate constant. Okay? So you can either get first or second order kinetics. But say we have this complex reaction, 5Br minus plus BrO3 minus plus 6H plus. How do we get the rate law for this reaction? So how do we get rate is equal to rate constant times the concentration of Br minus to the power of 1, BrO3 minus to the power of 1, and H plus to the power of 2? How do we get that? Okay, I think did I show that earlier? Where was it? Yeah, so how do we determine that? Okay. Well, it's actually easy to do. Right. Okay, so here it is. So we know that the rate law is equal to the rate constant times the concentrations of each of the species raised to some power. Okay, we know that. And we just assign them alpha, beta, and gamma, right? So we say, right, okay, so then the log of the rate is equal to log K plus alpha log Br minus, the initial concentration of Br minus, plus beta log the initial concentration of BrO3 minus, plus gamma the initial concentration of H plus. Okay? And then we can say, like, okay, so log rate is equal to alpha log Br minus, original concentration Br minus, plus all of the rest. Okay? So, and now we can say, right, y is equal to mx plus c. Okay? So if we keep then the concentration of BrO3 minus constant, H plus constant, and do a series of experiments where we change the concentration of Br minus only, we can get the dependence on Br minus. So we can, that's the initial rate method. Okay? So we measure the rate. So we get log of rate. We plot log of rate versus log BrO minus. And we should get a straight line, the slope of which is alpha. Okay? And then we do the same again, where we keep the concentration of Br minus constant and H plus constant, and we isolate BrO3 minus. And we can get beta. And then we do it again with H plus. Okay? We vary the concentration of H plus and keeping the others constant, and we can get gamma. Okay? And that way we can get alpha, beta, and gamma, the dependence. And we find that alpha is 1, beta is 1, and gamma is 2. Okay? Okay, and here's a simple example. Okay? And you can actually do this in your head while we're doing it, so you can see how it works. Okay? So we have 2 moles of NO plus 2 moles of H2 gives us N2 plus water. And we know that the rate is equal to the rate constant times the concentration of NO to the alpha times H2 to the beta. Okay? And here we do 3 experiments. Okay? The initial concentration of NO stays constant in the first 2. H2 decreases by a factor of 2. The rate decreases by a factor of 2. Okay? And then in the third experiment, the concentration of H2 is the same as in the first experiment, but NO concentration is half. But the rate constant decreases by a factor of 4. Okay. So we have to deduce the orders with respect to NO and H2, and then calculate the rate constant. Okay, is the mission. Okay. So what is the dependence on NO? NO, it's second order. Where did you get second order from? It's correct.
The rate changes by
Yeah, it's a square relationship. Okay, so it depends on the square of the concentration. Okay, so you double the concentration, the rate changes by a factor of 4. Okay, so it depends on the concentration squared. Okay, and what about on H2? First order. You double the concentration, the rate constant doubles. Or, sorry, the rate doubles. Okay, so the order with respect to H2 is 1. Okay, so we have the rate is equal to the rate constant times NO to the power of 2, H2 to the power of 1. Okay, and you can see that it's pretty simple. Okay, and then you have the rates, you know the concentrations, you can work out the rate constant. So you can work out 3 rate constants and get the average. Or if it's pretty perfect experiment, they'll be the same. Okay, but nothing's ever perfect. All right, so you can get the rate constant. Or you could plot them and get the slope. Okay, so how would we measure the original or the initial rate? Okay, so say we have A and B reacting to give us products P and Q. Okay, and we have lots of A and B at the start, and of course we have no P and Q. What would we choose to monitor the rate of reaction if we had a choice? Yeah, but you measure, okay, the concentration, but which species would you choose? If you wanted to measure the rate of that reaction, A plus B giving us P plus Q, which species would you choose to monitor? Yeah, yeah. So it's easier to keep track of the products than the reactants, okay? Because there's none. Now, that's assuming you have equal sensitivity to the detection of all the species, okay? You would, probably the best answer would be whichever one I'm most sensitive to would be the one that I would monitor. But let's assume that you have equal sensitivity to all 4. Which one then would you choose? And it would be best to choose one of the products rather than the reactants, because you have no product at the start. So any change, any appearance of product, you'd be able to monitor. Whereas it's harder to follow the decrease in the concentration. I don't know whether it's the same, but I always think of it, you know, at the start of the month, you've just been paid and you're flush, and a $5 here and a $10 there isn't a lot. But at the end of the month, a $5 here and a $10 there is a lot, okay? So I always kind of think it like that, okay? So when you've got nothing, a little is a lot, okay? So anyway, but ultimately, you get the same answer. You should get the same answer if you're able to measure things accurately, okay? This is all this is saying here. But if you have a choice, it's probably best to choose a product rather over a reactant. Okay, so another way, and this is very similar to the initial rates method, really. Okay, another way to monitor the rate of reaction is, and it's just a different way of looking at the initial rates method, in my opinion. They're the same in essence. Okay, so here we have IO3 minus plus 8I minus plus 6H plus. It's just a different reaction. It doesn't matter. And we know that the rate of this reaction is equal to the rate constant times the concentration of IO3 minus to the alpha, I minus to the beta, and H plus to the gamma. So again, it's dependent on each reactant raised to some power. Okay? But say we have just a thimbleful of IO3 minus, right? And a thimbleful of H plus, right? And we have the Atlantic Ocean full of I minus, right? And we react them together. Are we going to notice any change in the concentration of IO3 minus in the reaction? Okay? If we're going to react a thimbleful of the other two and an ocean full of IO3 minus? The answer is no. Okay? We won't see any change in its concentration, right? So if we add IO3 minus, then it's effectively constant. So we can rewrite the expression as the rate is equal to K prime times the concentration of I minus to the beta and H plus to the gamma, where K prime is equal to K times the concentration of IO3 minus to the alpha. Is that all right? And then we can do it again, and we say, okay, let's add also excess H plus. So we have the Atlantic Ocean full of IO3 minus, you have the Pacific Ocean full of H plus, right? And so you have a thimbleful of I minus. Now you'll see just the change in I minus. And we have the rate is equal to K double prime times the concentration of I minus to the beta, okay? Where K double prime is equal to K times the concentration of IO3 minus to the alpha and H plus to the gamma, okay? And so now we can measure the rate, or sorry, look at the concentration of IO3 minus with respect to time. And if we get, we can plot it. If we get log of the concentration of I minus versus time, we get a straight line. We know that beta is 1. If that isn't right, if it's not a straight line, we plot 1 over the concentration of I minus versus time, and it should be a straight line, and therefore it's second order. Okay? And we know beta is 2. And we do the same thing then for IO3 minus. We isolate that by flooding the system with I minus and H plus. And then finally, you do it for H plus, isolating H plus, flooding the system with IO3 minus and I minus. Okay? And that way you can get the orders with respect to each of the species. All right? So that's isolation or flooding and how you can measure the rates. Okay. So that's just measuring then the rate and getting the rate law of complex reactions. Okay? So one thing I want to ask, what are the chances that this would happen in one step? That you'd have one IO3 minus, 8 I minuses, and 6 H pluses all react together at the same place and the same time? Yeah, impossible. It's impossible. Okay? So it just can't happen, right, in one step. So that reaction, you know by just looking at it, is not elementary. Okay? If it is elementary, it happens as written. Okay? So it is not elementary. Okay. So, but what about the rate law for elementary reactions? What if it is elementary? Then you actually can use the law of mass action. Okay? So you use the stoichiometric coefficient, in essence. Right? So if we have A given us products P and Q, then we can write the rate is equal to the first order rate constant times the concentration of A raised to the power of 1. We can write that. We know it's elementary, and it happens as written. Okay? A plus B gives us C plus D. The rate is the second order rate constant times the concentration of A to the power of 1 times the concentration of B to the power of 1. And for this reaction, the rate is the third order rate constant times the concentration of A squared times B to the power of 1. Okay? So they're just three simple examples, okay? So, and what about molecularity of reactions? What is a unimolecular reaction? A unimolecular reaction, A gives products P, okay, and the rate is first order. It's equal to the rate constant times the concentration of A to the power of 1. Okay. Bimolecular collision, A plus B giving us products. And the rate is equal to the second order rate constant times the concentration of A to the power of 1 times B to the power of 1. What about 2A giving us products? Or A plus A, if you want to look at it like that, giving us products. Is that first order or second order? Is that unimolecular or bimolecular? It's bimolecular. It's bimolecular. Okay? So 2A giving us products, or A plus A, if you want to look at it like that, it's bimolecular. Okay? And thermomolecular, A plus B plus C giving us products, the rate is equal to the rate, third order rate constant, concentration times the concentrations of each of the species raised to the power of 1. Okay? And again, you could have 3A here, or 2A plus B, or whatever, as a thermomolecular. Okay. And for elementary reactions, no other reactions are feasible. It's statistically highly unlikely or that any more than 3 species are going to collide in the same place at the same time. And actually, other than bath gas reactions, so in chemical kinetic mechanisms, we will have reaction, and I'll be talking about this either later today or tomorrow, but certainly very soon, okay? We say H plus O2. This is the most important reaction in combustion. So if you don't learn anything else for the week, just learn this, okay? H plus O2 gives O plus OH, okay? So this is bimolecular, okay? And it occurs as written, okay? But we have a competing reaction at certain temperatures and pressures. We have H plus O2 plus M gives HO2 plus M. And now this is thermomolecular, okay? H plus O2 plus M, where M is all the molecules that are in the system, including oxygen and the diluent, okay? Argon or nitrogen or whatever your diluent gas is, okay? So that's thermomolecular. But typically, other than reactions like this, okay, typically in chemical kinetic mechanisms, if I have 3 species in a reaction, I provide the rate as 0, the rate constant as I included as being 0. So even for thermomolecular, other than this type of thermomolecular reaction, we typically assign a very low rate, 0, okay? And so, yeah, I'll leave it at that. Okay, so why is it, this was the first example that I gave for the rate law of reaction. We said it was 1.5 order, okay? So CO plus Cl2 giving us CO, Cl2. And I have an X through this. It does not directly give, okay? It does happen. But it's determined by experiment that the rate law is the rate constant times the concentration of CO to the power of 1, Cl2 to the power of 1/2. So if we look at this expression, we can see straight away that this reaction is not elementary. It's not first order with respect to both of the reactants, and therefore cannot be elementary. Okay? It's 1.5 order. Okay? What if it was? What if it was CO to the power of 1 and Cl2 to the power of 1? Could we then say it is elementary? Yeah. So somebody said maybe, and that's the right answer. It may be elementary, but may not. Just because it's first order with respect to both, you cannot assume that, yes, it is. It might be an indicator that it is, but it's not proof positive that it is. Okay? And I'll talk about that in the next slide. Okay? Well, actually the slide after the next one, but anyway. Okay, but actually, what happens here is that there's a mechanism. And the system, there's a 4-step process for this reaction, actually. It's not elementary. Okay? So what happens is Cl2 decomposes to give 2 chlorine radicals. Okay? And then a chlorine radical reacts with CO to give COCl. Okay? And then COCl reacts with Cl2 to give COCl2 plus Cl. So there we're getting this. And now the Cl that's left over here recombines with the Cl that's produced here, and we get Cl2 back. Okay? So we have these 4 steps comprise the mechanism for the reaction. Okay? So if we assume that steps 2 and 3, so these are reactions 2 and 3, are slow in comparison to the Cl2 recombining to give us 2Cl, or decomposing to Cl, and vice versa, the recombination. So this is in fast equilibrium, in other words. Okay? Then we know that the equilibrium constant is equal to the concentration of Cl squared all over the concentration of Cl2. Okay? Or then the concentration of Cl is the square root of the equilibrium constant times the concentration of Cl2. Okay? Of both of those. Okay? And if we go then back to reaction 2, the rate of this reaction is its rate constant times the concentration of Cl times the concentration of CO. Okay? So the rate of that reaction is equal to the rate constant times the concentration of CO times the concentration of Cl. But what is the concentration of Cl? The concentration of Cl is the square root of the equilibrium constant times the concentration of, or the square root of the concentration of Cl2. Okay? So this is the change in concentration of CO with respect to time. So we predict that the observed rate constant for the whole process is equal to the rate constant for reaction 2, this is, okay, times the square root of the equilibrium constant for the Cl2, giving us 2Cl equilibrium. Okay, that's what we predict. But how would we prove it? I don't know if I did this really that well, but how would you prove that this is true? Okay, the rate constant for this, so this rate constant is actually equal to the rate constant for this reaction times the square root of the equilibrium constant for the Cl2 equilibrium. How would you prove that? Well, what you do is you measure the rate constant for the overall process, right? That's what you observe, okay? So you have the rate constant for the overall process. And then and presumably you know the equilibrium constant for the Cl2 given us Cl equilibrium, or you determine it. And then you determine the rate constant for this reaction. So you determine the rate constant for the Cl plus CO reaction. And if that is equal to, if that times the square root of the equilibrium constant is equal to the rate constant for the overall process, then this 4-step mechanism is the mechanism for that reaction, which it is. Okay? So that's how it was shown. Okay? Okay, I haven't got it, but I showed earlier H2 plus I2 giving us 2HI. That was second order. So the rate was equal to the rate constant times the concentration of H2 to the power of 1 times I2 to the power of 1. It was assumed for many years that that reaction was elementary. It's not. Okay? It's not. There's a mechanism for that. And it just happens that the mechanism turns out, or the orders with respect to H2 and I2 are 1 and 1. But it isn't elementary, actually. Okay? And it's a pretty famous reaction for that reason. Okay? So you can look that up yourself if you're interested. Okay? It was determined, I think, in the 70s that it wasn't elementary. But it was assumed up to that it was. Okay? So here's just another example. We have acetaldehyde CH3CHO, giving us methane plus CO. Okay? And that occurs in 90% yield. So there isn't a three-centered elimination reaction where this hydrogen atom hops over to this carbon to give us methane and CO. That isn't what happens. Okay? So what does happen? Okay? So what may happen, we can break this CC bond. We get a methyl radical and formal radical. The methyl radical can abstract the aldehydic hydrogen atom to give us methane plus this radical, and that radical can decompose to give us another methyl plus CO. And then the two methyls could recombine to give us ethane. Okay? So actually, for this process, which does produce methane and CO in high concentrations, but we also see traces of ethane, hydrogen, acetone. So if a methyl recombined with CH3CO, you'd get acetone. Acetone is CH3COCH3, okay? And other products, okay? And we see these. So HCO can decompose to give us CO plus H. And then H can abstract a hydrogen atom to give us H2. Okay? So you can easily explain through a series of different elementary reactions the process for CH3CHO decomposition to methane primarily and CO. But it doesn't happen in just one step. The hydrogen doesn't just migrate to the next atom over producing methane and CO. Nice and simple. It's not. Okay? Right. Why? Because the activation energy for that process is very high. The activation energies and the rates for reactions of these other reactions are lower, and hence it has to go through those rates, those steps. Okay? If this was easier, it would do that. Okay? It's not. Okay? And we'll be talking about that a little later. Okay. Okay. And so this is really what I'm alluding to. Okay? So if we look at this species, ethyl chloride, giving us ethylene and HCl. Okay? And we measure the rate of reaction. How do we measure it now? I want it to be clear in your head and very crystal clear how this is all done. Okay? So what you would do is at 700 Kelvin, you keep the temperature constant, and you would you'd put C2H5Cl into some reactor and measure its concentration as a function of time. Right? That's what you do. Okay? And you then plot log of the concentration versus time, and you'd measure the rate constant for its decay. Right? Be first order. If it's elementary, it'll be first order. Okay? And this minus the slope of the line will be the rate constant. So you measure that. The slope of the line is 6.1 times 10 to the minus 5 arbitrary units, okay? Or per second, sorry, okay, at 700 Kelvin. Then you do it again at 727 Kelvin, and you measure that it's actually 30 times 10 to the minus 5, okay? And then you do it again at 765, and you measure that it's actually 242 times 10 to the minus 5. So it's actually not constant. The rate constant isn't constant. It's a contradiction, right? It is constant at a temperature, a condition of temperature and pressure, but it changes with temperature. And you can see that it changes a lot with temperature. So you just increase the temperature by 27 Kelvin, the rate changes by a factor of 5. Okay? You increase it again up to 765 Kelvin, and the rate changes by a factor of 8. Okay? So the conclusion is it's very sensitive to temperature. And a rule of thumb is the rate approximately doubles for a 10K rise in temperature. Okay? Now, that is actually a good rule of thumb for biological processes. I'll talk about that a little bit later, okay? And I'm going to do a little derivative later on that, okay? So just bear that in mind for later, okay? So the rate approximately doubles for a 10K rise in temperature, okay? That's only true at one condition, okay? We'll talk about it a little later. Okay, so the details of temperature dependence. Hood in 1878 said, okay, he was looking at it and he said, look, the rate constant is equal to some pre-exponential A factor times the exponent of minus an activation temperature all over T. Okay, and Arrhenius, 1889, said the rate constant is equal to pre-exponential A factor times the exponent of minus an activation energy over RT. Okay, is what we use. So A is a pre-exponential A factor, E is an activation energy, R is the gas constant, where T is the temperature, obviously. Okay, and so if we look at the rate of reaction, we see here, let's look at the magenta line and the blue line. The magenta line and the blue line, they're coming up at about the same temperature. So they have about the same activation energy. But the magenta line then rockets up faster than the blue line. So its frequency factor is a bit higher, okay? So these would have very similar activation energies, but the frequency factor for the magenta is higher than for the blue, okay? But you can see that for the green one, the activation energy is a little bit higher, okay? But also the frequency factor is a little bit lower, okay? But it starts to come up again. Then it reaches kind of a plateau and decays away. What's happening with the green one? What happened there? So we're plotting rate of reaction versus temperature. Pardon? Dissociation? Is that what you said? No. Pardon? No, it's not. No. You just killed the reactant. Okay? You killed the reactant. You increased the temperature so much that you killed it. So it must have been some biological process. And you fried. You fried him. and so the rate increased. He's happy to react. But then you've just killed him. Okay? So for biological processes, don't increase the temperature too much. Okay? Yeah. Okay. Okay, so so I was asked, how am I differentiating between pre-exponential A factor and activation energy when on this graph? Okay, so if we look here, the blue line and the magenta line, they're coming up at about the same temperature. If they come up at around the same temperature, it means they must have the similar activation energy. Okay, but this comes up then thereafter much faster than the blue line. Hence, the frequency factor must be quite a bit higher for the magenta one relative to the blue one. Okay, so that's where it's coming. I'll come back to that a little later because I have a nice graph that depicts this a little bit better. Okay, and I'll come back to it. Okay, but that's why I said that. Okay, so but let me come back to that a little bit later. Good question, right? Okay, and actually, the undergraduate students that I teach, they like this. So in Japan, the cherry blossom front is very important to the Japanese people, right? And it happens in springtime when the temperature rises, the land warms up, then the cherry blossom comes into blossom. But actually, if you look at, there's an equation that will predict the cherry blossom front and when it's going to happen. But it's actually an Arrhenius type equation. okay? And I talk about this with my students. In Ireland, I think last year, and certainly it was even worse about, I don't know, 7 or 8 years ago, we had very cold springs. And the farmers typically put the animals, the cattle and sheep and so on, out to graze around April time, you know, end of March, early April. But they couldn't put them out until May, mid-May in those years because there was no growth. It was cold. And so the rate of reaction is exponentially dependent on temperature. The temperature was too low, and hence the rate of growth was very slow. So the growth of grass, so it's the same in anywhere, in America or anywhere, okay? The growth of plants is dependent, exponentially dependent on temperature. It's a Arrhenius expression, okay? And this cherry blossom front is the same. Okay, so that's on Wikipedia if you want to go and have a look at it. It's just a nice thing. Okay, so here is a picture of Arrhenius, okay? And here's these equations. So the rate constant is equal to A e to the minus EA over RT, okay? And so we have log K is equal to log A minus EA over R times 1 over T, okay? So we had those three rate constants. We were able to determine them by looking at plotting log of the concentration of decay of the species versus time at each of the three different temperatures. We measured them. And now if we take log of the rate constant at any temperature versus 1 over temperature, we can get a straight line, the slope of which is minus EA over R, and the y-intercept is log A. And from that graph, we can get the Arrhenius parameters, A and EA. Okay? And we know the rate, we can then get the rate constant as a function of temperature. Okay? And interpret it over the range of whatever temperatures that we can measure. Okay, accurately. Okay, so here's such a graph. So we have log of the rate constant on the y-axis versus inverse temperature on the x-axis in Kelvin. Okay? And the slope of which is minus 22,550, from which the activation energy is 188,000 joules per mole, or 188 kilojoules per mole, okay? And the y-intercept here is 7. So it's the inverse of 7. Okay, what's going on here? The intercept is 27.602, but it's 7. There's an error here. Okay, so I do this with my undergrads. I hope you know better. Okay, it's at x is equal to 0 is the y-intercept. Okay, so always the y-intercept is at x equal to 0, so it's a way off over there. So the y-intercept is 27.602, so the frequency factor, A factor, is 1.1 times 10 to the 12 decimeter cube per mole per second. Okay, and we have the slope here is 188 kilojoules per mole. So you can get your A factor and activation energy, okay, by measuring rate constants at different temperatures, okay? And if you use this form of the expression, log of the rate constant versus 1 over T, you can get your frequency factor and your activation energy, okay? Nice. Okay. So typically, experimental activation energies range from 0 to about 400 kilojoules per mole. Okay, so we were talking yesterday, CH bond, primary CH bond, 101 kilocalories per mole. Multiply that by 4.184, you're talking about 420. Okay, so to break a CH bond, about 420 kilojoules per mole. Okay, a CC bond is about 368 kilojoules per mole. So here, ethane giving us 2 ethyl radicals, 368 kilojoules per mole. It's lower, but it's still substantial. Okay? To abstract a hydrogen atom from HCl, we only need an activation energy 19 kilojoules per mole. Okay? So there's a range of activation energies that we can have, from 0 all the way up. Okay? Okay, and so this is now getting back to the question that you asked a little bit earlier, okay? So here's here's the thing. In consecutive reactions, the slower step usually determines the overall rate of reaction. Okay, so diethyl adipate is hydrolyzed in 2 steps. So we have diethyl adipate gives some sort of an intermediate B and then a product. Okay, the Arrhenius equations are, the first step, we have this expression 3.6 times 10 to the 6th times the exponent of minus 5,080 all over T. So it's actually nice, and typically nowadays, even when I'm publishing papers, I'll put in an activation temperature. And that way, you don't have to worry whether the units are joules or calories for the activation energy, okay? So we're just putting in an activation temperature there. So just bear that in mind. So we've already divided by R, be it 8.314 or 1.987, depending on what units, okay? And then the second step is 8.8 times 10 to the 5 times the exponent of minus 4,010 all over T, okay? So here we have 2 expressions. Here, the frequency factor is higher, but also the activation energy is higher, okay? Here, the frequency factor is lower, the activation energy is lower, okay? So which step is rate determining if the reaction is carried out in aqueous solution at atmospheric pressure, okay? And here, I've plotted them. And I should really plot them. I should plot the red line as a blue line and the blue line as a red line. But anyway, it's plotted the way it is now, and that's it. Okay? Because I like to have the visual, which helps. Okay? So anyway, here we plot log K versus inverse temperature. And this is getting exactly to what you asked. So if we plot this rate constant expression, 3.6 times 10 to the 6 times the exponent of minus 5,080 all over T, we have, okay, so you can see here, look, the slope here is smaller than the slope here. Okay, so you can see the red line, the slope is smaller. Okay, but the activation energy is lower here. Okay, but the frequency factor is lower. So at lower temperatures, actually, the rate constant is faster with the lower activation energy than the one here with the higher activation energy. And that makes sense because it's exponentially dependent on the activation energy all over T. So if we have a higher activation energy, therefore the rate constant is lower at low temperature. Okay? But you can see here there's a crossover. So around, what is it, about 800 Kelvin, the 2 rate constants are equal, right? And then above that, now the activation energy isn't as important because we're higher in temperature. The activation energy isn't important, and now the frequency factor becomes dominant. And the frequency of this reaction is higher than the frequency of this one. So now this reaction becomes faster. So the answer to this question is, which step is rate determining depends on what temperature you're at, right? If you're at a temperature below 800 Kelvin, okay, this reaction is rate determining. If you're at a temperature above 800 Kelvin, this reaction is rate determining. Which the rate determining step will be the lower one. Okay? So I think that answers the question. Okay? And I do this deliberately, this particular example. I actually don't think the numbers were like this. I sort of made them up so that you could visually see the crossover, and that it's, you know, it depends on activation energy and frequency factor. Okay? So a high activation energy kills you at low temperature, right? And at high temperatures, frequency factors dominate. Okay? So to go back to what I was talking about yesterday, the CC bond is weaker than a CH bond. Okay? So unimolecular decomposition reactions of molecules, typically up to 1800, 1900 Kelvin, CC cleavage for hydrocarbons, CC cleavage dominates over CH cleavage. But actually, above about 1900 Kelvin, CH cleavage dominates over CC cleavage. Why? Because now the activation energy for CH cleavage can be overcome, and the frequency for CH cleavage is higher than CC cleavage. Okay? But for most applications for hydrocarbon combustion, okay, CC cleavage dominates. So if you see any of the Stanford shock tube data or any of the data from any fuels from shock tubes, typically unimolecular decomposition of CC. And if there's an oxygen atom in the molecule, CO bonds are weaker than CC bonds, which are weaker than CH bonds. So the weakest one is going to cleave first, the lowest activation energy. Okay, I'm going on a little bit. I hope that makes sense. Okay, just watching the time. Okay, so remember at the start I said a good rule of thumb is that the rate constant doubles for a 10K rise in temperature. Okay, well, that's true only at one activation energy. Okay, it's only true at one activation energy. So what is the activation energy of a reaction for which the rate constant doubles on going from 20 degrees C, we'd say room temperature, to 30 degrees C? Okay, and so we have the Arrhenius expression, K is equal to A e to the minus EA over RT, and we have then K1 is equal to A e to the minus E1 over RT1, and we have K2 is equal to A e to the minus EA over RT2. And if we put one over the other, we get this expression. So we have K1 over K2, the A's cancel, and we have EXP minus EA over R times 1 over T1 minus 1 over T2. Okay? And so therefore we have log of K1 over K2 is equal to minus EA over R times 1 over T1 minus 1 over T2. Okay? And so if we then just substitute in the values, okay, we have log of a half is equal to minus EA over R times 1 over 293.15 minus 1 over 301.15. We do all the mathematics, and the activation energy is 51.2 kilojoules per mole. Okay? So that is the activation energy for which the rate of reaction doubles for a 10K rise in temperature, going from 20 to 30. Okay? But it's only at that activation energy. Okay? Why is it, though, a good rule of thumb? Okay? And because actually, for a lot of biological processes, the activation energy ranges from about 45 to 55 kilojoules per mole. And that's pretty much slap bang in the middle of that. Okay? So that's why it's a good rule of thumb. Okay? So a lot of biological processes have an activation energy of about that value. Okay? Yeah?
And I guess for the...
Yeah, exactly. Yeah, exactly. Okay. And so this one I like. Okay? So now I have the right arrows. Okay? Because I did this one myself. Okay? So we go back to this A giving us B. Okay? So A is in equilibrium with B. Okay? And I'll finish at this. We'll take a break after this one. Okay? So if we look at kinetics, the rate in the forward direction is equal to K forward times the concentration of A. Okay? And that's typically what we say the rate is equal to, because we're only looking at that very early stage. Okay? But if we're real or honest about it, okay, and we look at the whole picture, okay, the rate in the reverse direction is equal to K reverse times the concentration of B. Okay? And B becomes appreciable at a certain period of time. Okay? So at equilibrium, the rate constant in the forward direction times the concentration of A at equilibrium is equal to the rate constant in the reverse direction times the concentration of B at equilibrium. Okay? That's, I think everybody agrees with that. And we know that then K forward over K reverse is the concentration of B at equilibrium, all over the concentration of A at equilibrium, and that's equal to Kp. Well, it's actually equal to Kc if it's concentration. But Kp is equal to Kc in this case because delta N is equal to 0. Okay? So we okay? Does everyone know that? Okay? Do I? Okay, I won't. Okay. Pardon?
Sorry, can you repeat that?
Here, Kp is equal to Kc because delta N is equal to 0. I can do that on the board very quickly for people. Okay. I'll just do it here. Okay, so we know PV is equal to N RT. Okay? So P over RT is equal to N all over V. And that's equal to concentration. Okay? Number of moles per unit volume is concentration. Okay? So P over RT is equal to concentration. So this is one thing I always say to my own students. Don't ever forget this. This is very handy to remember. Okay? The pressure over RT is concentration. Okay? So if we have A gives B, for instance, or, well, let's just take an example. A plus B gives C plus D. Okay? We have Kc is equal to, I'll write Kp first. Kp is equal to the partial pressure of C to the power of C times the partial pressure of D to the power of D, all over the partial pressure of A raised to the power of A times the partial pressure of B raised to the power of B. Okay? And we have Kc is equal to the concentration of C to the power of C, D to the power of D, all over the concentration of A to the power of A times the concentration of B to the power of B. Okay. Okay. But we know that P, we can write this, P is equal to concentration times RT. P over RT is concentration, or P is equal to concentration times RT. Okay? So I'm going to rub that out. So this is equal to the concentration of C to the power of C times RT to the power of C times the concentration of D to the power of D times RT to the power of D, all over the concentration of A to the power of A times RT to the power of A, and the concentration of B to the power of B times, RT to the power of B. Okay? And, okay, I'm looking here now. This is equal to the concentration of C to the power of C, D to the power of D, A to the power of A, B to the power of B, times RT to the power of C plus D all over A plus B. Okay? C. Oh, well, yeah, but okay. If you want to do it like that. Is that all right? Okay? Which is times RT to the delta N. Okay? So what is this? Kc. So we have Kp is equal to Kc times RT to the delta N. Okay? Is that all right? It was worth doing. The whiteboard is very limited, I'm sorry. So it's hard to. Okay, and in this case, the change in number of moles is 0. Okay, so Kp and Kc are the same. Okay, but by definition, we need to use Kp, even though we're talking about concentrations. So we're flip-flopping a little bit. Okay, but we can, because delta N is 0, they're interchangeable. Okay, so we know then Kf is equal to Af e to the minus Ef over RT, and Kr is equal to Ar e to the minus Er over RT. All right? And so we know Kf over Kr is equal to Kp, and that's equal to Af over Ar times the exponent of minus E forward minus E reverse over RT. Is that okay with everybody? There's nothing unusual there. So this is all from kinetics. Okay, but what about thermodynamics? Okay, from thermodynamics, we know that Kp is equal to the exponent of minus delta G over RT. All right? And so that's equal to the exponent of delta S over R times the exponent of minus delta H over RT. Is that all right? We're just, everybody happy with that? Okay. And so from kinetics, we have A forward, Kp is equal to A forward over A reverse. So we can say A forward over A reverse is equal to the exponent of delta S over R. Okay. And E forward minus E reverse is equal to delta H. Okay? And I think that's just showing you the link between kinetics and thermodynamics. Okay? I think it's a really cool slide. But okay? But it really just illustrates the relationship between kinetics and thermodynamics. Okay? And how the two are linked. So there is no break in that, A decreases in time, B increases in time. There is no break. There's no solid line between kinetics and thermodynamics. They're interlinked, and this is how they're interlinked. Okay? Okay, that's probably a good place to take a break. Let's come back. I don't know, what time will we come back? 20 past 10? Quarter past 10? 20 past?